Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be talking about mass calculations. So I guess we don't really need to explain what the what is within mass. Well, mass is mass, to put it simply. I mean, we don't really need to explain too much there, but I guess why are we doing this? Well, primarily we're going to be trying to find the center of mass of objects. So in this section, we're going to be given possibly complex shapes in which, well, where's the center of mass of this complex shape? And, we might be able to intuitively predict it, but knowing exactly where that is may be a powerful tool when using applications of it. And obviously, overall mass is going to be another big use of mass calculations in Calculus 3. So I guess the next question is, how are we going to do this? Well, if a region E has a mass density of rho of xyz, this is going to be three-dimensional, well, we can essentially solve for the mass by multiplying that density by the change in the volume. So what am I trying to say here is, well, we're used to the formula of mass is equal to density times volume, but now we're doing complex shapes. Density is not always going to be constant now. So in the past, perhaps we're used to density being a constant, and that makes it easy for sure. But what if we had, per se, a cloud of gas that it's thicker in the center, therefore it has more density in the center compared to on the outskirts, or maybe a metal plate that's heavier at one edge than the other. So essentially, mass density, it's function now. It's a function. Therefore, we cannot just use the simple mass is equal to constant density times volume. That's not how it's going to work anymore. These two things are going to be variable now. And similarly, if we have a region R with a mass density of rho of xy, well, this is going to be two-dimensionally, but it's a similar concept. We're going to have a double integral wherein we're integrating that mass density over with our differential being dA. That's going to be the mass of our region R. Once again, I have to reiterate that these densities are not going to be constant like they were in the past, perhaps. They may be constant in some cases, and I think we'll talk about that today, but in general, these densities are no longer going to be constant. So essentially what we're doing is we're finding the total mass by chopping our shapes into small cubes, small whatever. We're going to find the mass of each piece with that mass density, and then we're going to add it all back up together. So they're one-dimensionally is not really something we're going to be dealing with a lot, but you could kind of think of it as kind of like a scale. So it's like a one-dimensional scale. I'm going to pretty much glaze over this because we're not really ever going to be doing one-dimensional mass calculations within Calculus 3. So I guess this is more to introduce this concept. So this right here, this is the notation for that. It's basically the mass calculation for this it's going to be that rho times our differential, like we said, from a specific set region, and then that is going to be under our total moment, with that center of mass one-dimensionally being just that, right? So the question is, I guess, what does it look like when we're getting into higher levels, right? Well, okay, two-dimensionally, we're used to this. This is x and y, right? Now we're no longer just in one dimension. Now we're going to be getting into two dimensions here, so it's going to get a little bit more constant, or not constant, a little bit more tricky here, I guess you could say here. So it's pretty much a similar formula wherein we have the moment with respect to y over our mass for our x portion of our mass, and the moment with respect to x over the mass is going to equal our y portion. And perhaps intuitively we can understand that, well, what happens when we put both of these together? Well, what that is, that's going to be the center of mass. That is the coordinate where we have our center of mass in a two-dimensional area. Once again, it's pretty much the balancing point of an object is our center of mass, right? So once again, perhaps intuitively we can understand where it could be, but it's useful to know exactly where our center of mass is going to be. And three-dimensionally, finally, we're going to have a z component now, wherein we take the moment over of all of our pieces, right? So in our x portion, I suppose you could say we're gonna be taking the triple iterated integral of x multiplied by that mass density over the total mass. So this is kind of said as a moment with respect to y and z over the mass, and it's pretty repetitive on the other two as well. It's going to be these very similar concepts for these three, and I guess we can kind of guess, well, the center of mass is going to be these three placed into a coordinate system. So I believe that's all that we have to talk about right now. I guess maybe you may be asking exactly what a moment is. The moment is what it's distributed over. So whereas mass, we could conceptually think of mass already. Well, mass is essentially how much there is, right? Well, the moment might tell you where it's distributed, which is kind of why. Well, if we take where it's distributed over the total mass there is, well, then that's probably gonna tell you exactly where your center of mass is gonna be. Yeah. So let's see. Is there anything else I want to talk about? I don't believe there's anything I want to talk about until we get to an actual example, and maybe then I'll bring up this new point. But let's go ahead and go to our first example. I already graphed it out here. We're asked to find the center of mass of our region R, the set of x and y such that -1 is less than or equal to x is less than or equal to 1, and 0 is less than or equal to y is less than or equal to 1. So I already graphed this out for us. Well, we're going to have, this is going to be x is equal to 1, this is going to be x is equal to -1, this is going to be y is equal to 0, and this is going to be y is equal to 1. So, what are our formulas here? Well, we're trying to find our x and y, kind of hat. Well, how do we, what is the formula for this? Well, we just saw, well, our x is going to be the moment with respect to y over the total mass, and our y is going to equal the moment with respect to x over the mass. One thing that I would like to point out here is it's pretty conveniently enough, we can just find the bound once and it's applicable to all of the calculations that we're going to be doing. So that's pretty nice when we're actually going to be integrating these things. So I guess just to find the bounds, well, what is our dy? dy is going to go from 0 to 1. We kind of understand that. I mean, I guess I can draw it out here, but this is a pretty relatively simple shape. We're going to be entering from our y is equal to 0 and exiting from y is equal to 1. And similarly with our x differential, our bounds there are going to be entering from x is equal to -1 and exiting at x is equal to 1. So we found our bound. So I guess now the only thing we have to do is kind of extend it. So I like to break it up into little pieces. So first of all, I think I'm just going to go ahead and solve for the mass. And then I'll solve for the moment with respect to y right here. Then I'll solve for the moment with respect to x separately. And then once we put it all together, then we'll probably have our center of mass. Well, what is our m? Well, our mass is going to equal the double integral. The double integral of our density. Where's my, oh, I didn't even give the density. Oops. Our density is 2 minus y. Sorry. Alright, well, we have our density, but that's going to be 2 minus y. I just gave it to us there. We're going to use the basic order, dy dx. Well, we already solved what our dy is going to be. That's going to, the bounds on that one is going to be 0 to 1. And similarly, our bounds for x are going to be negative 1 to 1. We kind of drew that out there. So let's just go ahead and solve this. We're going to have the integral from negative 1 to 1 of 2y minus 1/2 y squared, evaluated from y is equal to 0 to y is equal to 1 dx. This is just going to be 2 minus 1/2. 2 minus 1/2 is just going to equal 3/2. Dx. When we take the integral here, it's going to be 3/2 x evaluated from negative 1 to 1. We're going to have 3/2 minus negative 3/2, which is going to equal 6/2, which is going to equal 3. Our mass is 3. Let's go ahead and solve for the other two. Let me actually move some of these calculations. Looks good. Keeping with our order, I said I was going to solve for my m sub y first. This is going to equal the double iterated integral over the same bounds, but this time we are going to be x times our density, 2 minus y, dy dx. Same bounds. Pretty nice that we only have to find the bounds once. Apologize. This is going to equal from negative 1 to 1 of 2xy minus 1/2 xy squared from 0 to 1 dx, which is going to equal integral from negative 1 to 1 of, well, this is going to be 2x minus 1/2 x. Which is going to equal 3/2 x dx from negative 1 to 1, which is going to equal 3/4 x squared from negative 1 to 1. Plugging in that, we're going to have 3/4 minus 3/4. That's going to be 0. Interesting. So I guess I'll explain this afterward, but there was definitely a shortcut I could have taken to tell myself, well, that's just going to be 0. Perhaps we can see it as is, but perhaps not. I guess we'll just go ahead and finish it, and then I'll explain afterward. Now solving for our moment with respect to x, that is going to be the double iterated integral over the same bounds from 0 to 1 and negative 1 to 1 of y times our density, 2 minus y dy dx. This is going to equal the iterated integral over negative 1 to 1 of, that's going to be 2y, that's going to be y squared minus y squared 1/3 y cubed from 0 to 1 dx, which is going to equal the iterated integral over negative 1 to 1 of 1 minus 1/3 dx, which is going to equal 2/3. Negative 1 to 1 of 2/3 dx, which is going to equal 2/3 x from negative 1 to 1, which is going to equal 2/3 minus negative 2/3, which is going to equal 4/3. Well, putting this together, we know that our x is equal to 0, and our y is going to equal 4/3 over 3. Doing some simple algebra here. 3 over 1, which is going to equal 4. Therefore, our center of mass oh, 1 over 3, sorry. Oops. 4/9. Our center of mass is going to be 0.4/9. Which is, let's see, where would that be? It's a little bit less than half of this, so I guess it would be around like here, I would say. Okay, moving on to our next example. We are asked to find the center of motion bounded by x is equal to y squared, x is equal to z, x is equal to 1, and z is equal to 0. The region D is uniform constant density. So I guess, first of all, let's start off by addressing the constant density. I know I just said earlier how like the density wouldn't always be constant, but I guess in this situation it is, which kind of makes it easier in a way. So basically, what is this saying here? Well, if the density is constant for both of our integrals here, well then that's going to make it a whole lot easier because, well, let's just say that we don't have to worry about integrating the density anymore. Oh, I guess it's better to explain it. So if we have some constant density, k, well, that density is going to be on the top and the bottom for our moment and our mass, meaning they're just going to cancel out. So I guess I'm just going to write it down real quick. So say we're trying to find x. Well, if it has constant density, then we can just pull out that k, take that double, triple integral, whatever, over some region of our x, dz, dy, dx, over that same density. Well, this is just going to be dz, dy, dx. So we don't even have to worry about the density anymore. We're just going to be integrating that x or the y or the z, the total moment, over the volume. I'm only doing this because, well, it's going to make our calculation kind of easier, and conceptually it's kind of important to understand that when the density isn't there, well, we can just pull out that density out of our total moment and our mass calculation, and it's going to be the exact same. It's going to cancel out. So I guess that's kind of my brief explanation of why. Well, okay, what are we looking for here? Center of mass, meaning we want to find our x, y, and our z. Well, our x is going to be equal to our moment with respect to y and z over the mass. Our y is going to be equal to the moment with respect to x and z over the mass. And our z is going to be equal to the moment with respect to x and y over the mass. So let's go ahead and calculate that mass first. I guess in this situation now, it's almost easier to say the volume. So I might even just cross this out and just put these as volumes for all of them, because that's pretty much what we're doing. We're not integrating anything with our density anymore. So let's go ahead and solve for that volume. Well, we're going to have some triple iterated integral of our dz, dy, dx. And this is our favorite shape here, as I keep saying. We know exactly how this works. Well, we're going to be entering from that z is equal to 0, and we're going to be exiting from that little slope right there. Well, that's going to be z is equal to x. Okay, now moving on. Well, what's our y bound going from? Well, it's going to be looking like it's going from, well, this the whole way. So that's going to be x is equal to y squared. So it actually may be easier to do dx dy, because then otherwise we're going to have to mess with our integral and make it kind of split even more. So I guess dx dy may be the more appropriate approach here. Well, what's that going from? Well, that's going to be going from our x is equal to y squared to 1, right? We're bounded by x is equal to 1 and x is equal to y squared, so that's pretty much where that's going to go from. And then finally, what are our bounds? Well, if our x is equal to 1, then that means we can just kind of solve 1 is equal to y squared, so then y is equal to positive or negative 1. Alrighty, let's go ahead and solve it now. Well, we're going to have the integral from negative 1 to 1 and the integral from y squared to 1 of, well, z evaluated from x to 0. That's going to just be x, dx, dy. Now we're going to be integrating from negative 1 to 1. And, well, let's actually not even do that. This is going to be 1/2 x squared from y squared to 1 dy. This is going to be equal to the integral from negative 1 to 1 of 1/2 minus 1/2 y to the 4th dy, which is going to be equal to 1/2 y minus 1/10 y to the 5th from negative 1 to 1. This is going to be equal to 1/2 minus 1/10 minus negative 1/2 plus 1/10. This is going to be equal to, what is that, 1 minus 2/10? It's going to equal 8/10, which is going to equal 4/5. That's our volume. Okay, now let's go ahead and solve our moments here. We're going to look for the moment of yz, moment of xz, and our moment of xy. Let's see, is there any symmetry that we can eliminate here? Well, okay, let's just kind of look at this intuitively. It's perfectly symmetrical about the x. I don't know. If it's perfectly symmetrical about that, well, on the y-axis, it's the exact same over here as it is over here, meaning, well, that moment with respect to x and z, well, that's just going to be 0. We can kind of deduce that. So our moment with respect to xz is going to be 0, meaning our y is going to be 0 in our center of mass. And once again, we can kind of intuitively kind of look at this shape and be like, okay, it's the same on both sides. Well, that means that it's going to be somewhere on the exact center. If it's a perfect mirror along the x-axis, then that means it's going to have to be along the x-axis, meaning that y is going to be 0. We are not going to be translating to the left or to the right at all. So I guess that's kind of the way you can think of it. Let's go ahead and solve for our m of y, z, our moment with respect to y and z. Same bounds here. This time we are going to be integrating with x, dz, dx, dy. This is going to be from negative 1 to 1 and y squared to 1 of, well, that's going to be x squared dx dy. Negative 1 to 1 y squared to 1 of 1. Oh, well, actually, I don't need to do that, sorry. 1/3 x cubed from y squared to 1 dy, which is going to equal the integral from negative 1 to 1 of 1/3 minus 1/3 x to the 6th dy, or x y to the 6th, sorry, dy, which is going to equal 1/3 y minus 1/21 y to the 7th from negative 1 to 1, which is going to equal 1/3 minus 1/21 minus negative 1/3 plus 1/21, 1/21. This is going to equal 2/3 minus 2 over 21. Multiply that by 7 right here. That's going to be 14/21 minus 2 over 21. Oops, 21, which is going to equal 12/21. Divided by 3, that's going to be 4/7. Okay. Let's see, what are we solving for now? We are solving for a moment out of x and y. Oh, man. I'm running out of space here. We're moving everything over. Oh, man, I did not grab all that, did I? Moving it all over. Well, our moment with respect to x and y can equal -1 to 1. Same procedure. I'm just going to blaze by this. Of z dz dx dy. We get the concept, I suppose. -1 to 1. Y squared to 1 of z squared. So this would actually be 1/2 z squared. So this is going to be 1/2 x squared dx dy. Which is going to equal -1 to 1 of 1/6 x third from y squared to 1 dy, which is going to equal the integral from -1 to 1 of 1/6 minus 1/6 y to the 6th dy, which is going to equal 1/6 y minus 1 over, what is 7 times 30, 42 y to the 7th from -1 to 1 here. Let's just do a quick little sanity check. Am I doing this right? I think so. This is going to be 1/6 minus 142 minus -1/6 plus 142, 1 over 42. This is going to equal 2/6, which is equal to 1/3 minus 2 over 42. Let's see. 3, 6, 9, 12. That is going to go into that. What is that? 3, 10, 13 times? 14? 14. I think it'll be 14 over 42 minus 2 over 42, which is equal to 12 over 42. Simplifying that, that is going to be, divide that both by 6, it's going to be 2 over 7. Putting this all together, it looks like our x is going to equal 4/7 over 4/5, which is going to equal 5/7. Or y, well, we already solved that. That's 0. Z is going to equal 2/7 over 4/5. Which is going to equal 5/14. So our center of mass is going to be 5/7/0/5 over 14. That is mass calculations in Calculus 3. Thank you very much.